afternoon, all. I'm delighted to be here, and thank you, Professor Amatani, to invite me to come here to give a lecture. And the subject, as you can see, is on the wind power in the UK, the existing situation, and also looking to the future. I understand from learning from Professor Amatani about the programme and from reading about the aims of the programme that many of you are not from engineering background. So I have tried to make the presentation as general as possible and to not make it too technical. There's only one equation, which is in the paper. So there will be some technical words, but which are good to know. Good to know the words, even if you don't know the detailed engineering principles behind the words, but it's good to know some of the technical words. And then what I've done, I've got this presentation, I think you have copies, and I've also written a paper to try and tell the story with a little bit more background. And then the other thing I've included in the paper, because wind power is going to be very big in the UK, it will have a big impact on the electrical system. So I've done a little bit of the history of the UK electricity system for you to understand how such systems evolve, how they can be flexible, and how they may look in the future. So there's a little bit of extra background information on the physical evolution of the electricity system in the UK, and also a little bit about the financial and commercial organisation, because it's very different from country to country how the electricity system may be a national body in some countries. In the UK, it's completely private with government regulation. So I've tried to include some information to put all of this about wind in context. So let's see. It's important to see wind power as part of an overall renewables strategy. It's not just about wind, it's about how wind will complement and work with other renewable technologies. In the UK, we have two quite distinct contributions from wind. One is onshore, and the other, because we are an island, is offshore. Talk a little bit about the cost of wind power. The cost is very important. I know some of you may be with economics background. You can do nothing without knowing what the cost is. We'll talk a little bit about how renewables is subsidised by governments in order to make it work quicker than otherwise because of the global emissions reduction targets. We'll look then about what I just talked about, how it fits into the electricity system, and finally, let's look further forward. Look to 2050. Let's see what things will look like in the UK. So what I've tried to do is to make everything oriented towards the UK. You can learn about many things about wind from many different countries and publications. So I've focused on the UK. And let's start with a little question. You shouldn't see the answer really here, because I'm making the question now. Who, where and when established the first house to be powered by wind-generated electricity?
If the student can give a correct answer, you offer the cup of coffee.
There's a prize. And here is a picture of it. It's a black and white photograph from a very long time ago, so it gives a clue. And you can see it's a vertical axis wind turbine. You know, most of the wind turbines nowadays are horizontal axis, but this is a vertical axis wind turbine. And the answer here is that it was a professor from Glasgow University in Scotland, and he built a wind generator in the land next to his holiday cottage in a place called Marykirk, and he charged batteries from there. Of course, the induction generator had recently been invented, Nikola Tesla. So electricity was a very new thing. But wind generation is not a new idea. But like we see with so many ideas, they're not always new, but whether they work and translate into practice in a big way depends on more than the idea. And usually you need the right place and the right time. So although the idea was back then, over 100 years ago, maybe only now is the right place and the right time for wind. So, what is the potential for wind generation in the UK? Here's Great Britain. Here is Ireland. I don't know if you're confused. Sometimes we call it UK. Sometimes we call it GB. Sometimes it's called England. Yeah, so there are three countries here: Scotland, England, and this is where I'm from, Wales. And this is Ireland. So the three countries here are Great Britain. And Northern Ireland is attached politically to Great Britain, and then you have the United Kingdom. Ireland, the Republic, is a separate country under the United Nations. But, okay, in comparison with mainland Europe, you can see where the very good wind speeds are. The red, 5 to 6 average meters per second speed. The north coast of Europe is also very good. So France, yes, Belgium, Netherlands, north of Germany, and look how good Denmark is. So it's no surprise that the world's largest wind turbine manufacturer is from Denmark. They were pioneers in the recent decades. The darker area is above 6, so very windy. And you can see that Scotland is very windy and a very good place for wind turbines. And you can see Denmark too. And the same, if better, will apply offshore. Because when you're onshore, the wind will pass over the uneven ground and create turbulence, which affects the ability to extract energy from the wind. And it's better out on the sea, where you have smoother flow of air without turbulence, so you can capture more efficiently energy from the sea. And that, as we'll see, is probably the key for the future. So what about realisation of wind energy in the UK today? Okay, the government's signed up to the protocols. The UK, as part of the European Union, is committed to produce. We've got a target for 2020, 15% renewable energy by 2020. Very ambitious. Very difficult to achieve this in heating and transport sectors. More easily achievable in electricity. So to meet 15% overall for energy in the economy, we need to get 30% from renewables by 2020 in electricity, which is very, very demanding, but achievable. How can this be achieved? People say, aren't renewables too expensive? The opponents of renewable energy always say, yes, it's a very nice idea, but it's too expensive. That may be the case in basic economic terms, but if we take into account the cost of the emissions, of the damage to the planet, then we cannot apply the simple microeconomic formulae. We have to look at the bigger picture, which is the governments have done. So we make subsidies. In the UK, it's called the renewable obligation. In the UK, the two main subsidies, the two main technologies which are subsidised are photovoltaic and wind. The other thing we can say to people who are saying that renewables cost too much is to realise it's a new technology in the sense of its modern incarnation. And with any new technology, costs fall when you increase the efficiencies of production, the technology matures. For example, photovoltaics have fallen by 50% in the last year. That's a remarkable reduction. People always said, oh, they're too expensive. You know, very, very expensive. Wind will also reduce. Wind turbines are getting bigger to increase load factors. The more that's produced will give you scales of mass production. So, like motor cars, if you buy a car like a Rolls-Royce or a Bentley, not many of them cost so much, but if we buy a car where they produce millions, the cost comes down, and the same will happen. They estimate, these are government departments and energy experts, economic experts, they estimate that onshore wind farms will be competitive with conventional gas turbine power stations within a few years. We're talking about less than 10 years. That's good news. So where do we stand now? Already we have 14.4 gigawatts of renewables overall in the UK. The maximum demand electricity in the UK is 60 GW. 60 gigawatts.
Same size of Tokyo Electric in Japan. Yes, Tokyo Electric, about 50 to 60 gigawatts.
Okay, yeah. So it gives you an idea, that's quite big. Onshore, at the moment, is the biggest, 5.3, offshore 2.5 already. So already now, wind power is set to become the big player in renewables. I'm showing here the picture over the last 20 years. You can study, but you can see that going back 20 years, okay, basically we had hydroelectricity. We have biomass plants, which are basically burning waste. Yes, it's a fancy word for burning combustible waste. That increased. That's rather than burying the waste, combustible waste in landfill sites, you can burn it, or produce, or rather get gas from it to burn it. But then wind, which is the green, is nothing back 20 years ago. It's starting. The green is growing. I put it as green because it's obviously green energy. It's increasing. So, 7.8 gigawatts from wind is not bad, but there are problems. The wind is variable. Everyone who talks about wind power who doesn't know anything about wind or electricity, they will always say, yes, but we have days when the wind is not blowing and we will have no electricity, so we can't use wind. That's usually the simplistic response. But as we'll see, it's not quite like that. So how do we make that bigger? We've got to meet the 60 gigawatts, and how do we address the issue of the fluctuation in wind generation? Let's have a look at what we have. Now, this is a map showing, okay, it's showing onshore and offshore, but we're focusing on onshore for now. The onshore are the red circles. Onshore wind farms in the UK. The existing offshore are the blue triangles. We'll come to those later. But as you can see, you saw the wind map from earlier. Doesn't this really show you a direct translation of the wind map? Where we have the farms, the bigger farms, are mainly on the western extremity in Scotland, where wind speeds are high. On this map, interestingly, they have eliminated Ireland. There is landmass there, but quite often with UK maps, Ireland somehow disappears. But it's not just that, it's there. It'll come back later. My wife is from Ireland, so it's good. It's important to say that there is a country there. I thought we'd show some pictures because, you know, we can have data and equations, but pictures are very nice. This is from my country, Wales. This is Neath Port Talbot. It's a beautiful countryside. And you can see this is an example of a 32 megawatt site, 16 turbines, 2 megawatts each, so they're very big units. 70 meter diameter, and the height here is 58 meters. We'll go to Scotland now, the far extremities of Scotland. You may have heard of the Hebrides, the famous piece of music written by Mendelssohn about the Hebrides. It's an island off the northwest coast, and here we've got 4 megawatts from three turbines here. Again, a beautiful part of the UK, the Outer Hebrides. And this shows you a kind of summary of the total installed capacity in the UK. So here we have Wales, Scotland, the most. Yeah, that's where the wind speed's the highest. Northern Ireland and England. England doesn't have much, considering the vast majority of people, you know, England dominates the UK's biggest population, but it's not the best place for onshore wind. Now, let's look at the cumulative capacity. I've stripped out the data from the other renewables. This is focusing on wind now. You can see 20 or so years ago there was nothing worth talking about, but we can see a very dramatic rise now up to this 5.8 gigawatts, or just over 5,000 megawatts capacity. Now, when we talk about the capacity of a wind turbine or a wind farm, and we give the unit in watts or multiples of that, so kilowatts, megawatts or gigawatts, we're referring to the maximum power. If wind speeds are high, that is the maximum power that can be delivered. Now, of course, the wind does change. It fluctuates, and some days we'll have very little wind or no wind at all. And a measure of the amount of energy that a wind farm produces as a proportion of the total theoretical maximum, the maximum being if the wind farm is on full output 24 hours a day, 365 days a year. So we have something that's called the capacity factor, which is the ratio of the energy actually produced to the potential maximum energy yield in 1 year. There are different ways of calculating the capacity factor, and sometimes it's called the load factor. You can measure it accurately from the energy, the metering, which is the most accurate. You won't tell a lie when you know what you're getting from the farm. Or you can do as I've done here. I've been just looking at the maximum powers, the rated powers of the generators, and there's a little equation in the paper which shows what I've done. And this is from published data, and you can see that the load factor is possibly increasing a little, but is around about, for onshore, it's around about a maximum of 30%. That's what we're getting in the UK. Now that means it takes account of regional differences. These are averages. It takes into account the fact that the turbine may be down for maintenance. Yeah. It takes into account that average wind speed for years will be different year by year. Sometimes you'll have a very windy year, sometimes you won't have a windy year. But it gives you a feel now, around about a third of the real maximum potential energy is realisable. It's not bad. We'll run through a few slides now to show the picture of what's happened in terms of size and numbers. 20 years ago, we had turbines. On the y-axis here, we've got individual turbine capacity in megawatts, or thousands of kilowatts. Down here in, say, 1992, up to the 2000, we had turbines of the order of a few hundred kilowatts. There's been a step change, and it's got big. Wind has got big, or the turbines have got very big. And now we're looking at onshore 3 megawatt turbines. So we've gone from 300 kilowatts to 3 megawatts. Big, much bigger machines. Much bigger machines, much bigger blades. The reason for that is that you can capture more efficiently the wind, the bigger the blade is. However, depending on the site, you may want to use smaller turbines for particular projects. So smaller turbines are still used. And now there's a spread of size of turbines. Numbers, okay, well that's interesting because the numbers have not really changed, you know. There was a very big wind farm back in 1992. Maybe we'll see some big super wind farms. This one here, Whiteley in Scotland, is Europe's largest offshore wind farm. It has 140 turbines, overall capacity 322 megawatts. Now we're beginning to get up to the scale of conventional power plant. In the UK, a conventional generating set at a fossil fuel thermal power station would be 660 megawatts, and maybe you have 4 of them. Now we're beginning with a whole wind farm to get into the same order of magnitude as an individual generating set of a conventional plant. I thought I'd show you a picture. Here it is, Europe's largest onshore wind farm. So you need a lot of area, a lot of space. And unfortunately, many people are against wind power. Many people think these are ugly. Many people think electricity pylons are ugly. A lot of people who like electricity think a lot of things to do with electricity is ugly. If only we took the electricity away for a week, maybe people will change their mind. Because in the emerging times when we had electricity, everyone was so grateful to have it. You know, my parents grew up without electricity. You know, they had candles and oil lamps, and they had to go and fetch water. You know, that was a different world, just in my parents' generation. But now people have different...
just like your air.
This is showing total site capacity, which is increasing. So numbers are not increasing, but capacity of turbines, that's Whiteley up there. And we'll have more like that. So what about the future? It's incredible, really, that I've started here with the existing capacity, 5.3 gigawatts. Under construction, 2.3. So I've got a cumulative total here to show how it's going. Pre-construction, that means that all the legal, commercial frameworks have been satisfied. We've got consent to build, planning permission, they've bought the land, but they haven't yet built it. 4.4 gigawatts in that, that's a lot. And in planning application stage, in other words, companies who have the finance make the application? 6.9. So we could have 19 gigawatts. Remember the UK target, the maximum demand is 60. Okay, so covered onshore. Let's now look at offshore. Slightly different picture, even more interesting. This map here is produced by the Department of Energy and Climate Change, via the Crown Estates. In the UK, it's funny, we're a very funny country. The coast and a distance of up to, I think it's 22 nautical miles from the coast, is owned by the Crown. In other words, the Queen theoretically owns it. So it's managed by what's called the Crown Estate. And the government then had to set up agreements with the Crown Estate in order to lease areas of the Queen's waters to companies. Now, ignore the pink for now, because this is the really big stuff that's coming later. That hasn't happened. We have had, with the Crown Estate, 3 rounds of offshore wind farm. Round 1 and 2 are quite small, and they're all dotted, very close to the coast. North Wales, Liverpool. I'm sure you've heard of Liverpool from the football club, yeah? And then round London, Thames Estuary, up to Ipswich. So a lot of these are, they're big, but nothing like these. So these have been built. Installed capacity, nothing in 2000. Okay? So much later in terms of starting. 2003, 2012 now, we've already got 3 gigawatts, the latest figures. Now let's do the same thing. Let's look at types of machines, the numbers, the total powers. You can see already that the turbine capacities are always big. 2 megawatts, 3, and now we're up to 5 megawatts per machine. So that's the first thing to note, is the scale has gone up. And if we're ever to get big numbers, we have to scale up. Numbers. Okay, at the moment, in the period 2000 to 2010, the numbers were fairly modest, 30 per farm. But now we can see the numbers are going up 100 and more. And in fact, the biggest has just been commissioned very recently. And this offshore wind farm, which now produces more power than the biggest onshore wind farm, we are now at 500 megawatts, half a gigawatt. Now we're really talking. That wind farm now is called Greater Gabbard, the name of it. And this is where it is. This is London. This is Ipswich, I mentioned before. Sizewell. Sizewell is where we have a large nuclear power station. So lots of big substations to plug in, you know. It's not exactly plug and play like our electronic components, but we have to plug it in somewhere, and this is a big nuclear power complex here. Still, interestingly, going in at sub-transmission level, so we'll talk about the transmission in a little while. Not at the highest voltage, but half a gigawatt, 140 turbines, each 3.6 megawatts, 26 kilometers offshore. So people don't have to worry about noise or visual amenity. It's out there, so there's less opposition. Obviously, there's a challenge to get the power here via cables. That's a big challenge. I thought some pictures of Greater Gabbard. I think it's absolutely beautiful. I don't know what you guys think. Beautiful. A nice sunny day. a cloudy day with some dramatic sunshine coming through the clouds. And I like this shot in particular. And at the moment it's the world's largest offshore wind farm. And it's now just operational, just in the last few months. And I've included this shot just to give you an idea now of size. We saw the professor's wind generator from Scotland, over 100 years ago, which he built himself in his back garden. Now we're talking about large-scale industrial production. We're cooking now, aren't we? We are cooking. And this is where the future lies for wind power. I haven't included a lot about the manufacturing details, but the big players in wind turbine manufacturing, the Danish company Vestas is still the largest turbine manufacturer in the world. I think 3 of the top 5 are Chinese manufacturers. Who else is there? There's Siemens. Siemens are big in wind turbine. GE in America. Mitsubishi, I think, produce turbines. So these are the big companies involved in the production. A lot of the offshore technology, I think one of the reasons the UK has taken the plunge is because there's a lot of skills from the North Sea oil industry that they've been able to. There's a workforce there which is highly skilled in offshore construction, and that has been an advantage in being able to have the confidence to build good structures on time. I mean, I'm focusing on the electrics here, but there's a lot of civil engineering and mechanical engineering. So, what's happening in the future? Now, this is amazing. This is really... Look, operational, 3 gigawatts. Under construction, 1.5. Round 1, round 2, round 3. Round 1 and round 2, remember, we're very close to the coast. Relatively small areas. 1.4. Pre-construction, another 2 gigawatts. And now, in the planning, this is what we got. This is round 3. These are the really big areas that we saw in the North Sea. For example, the area called Dogger Bank. Planning 5. We have a projection, and this is only in terms of projects, actual projects that have been designed or operational, almost 14 GW now. And there's many, many, many more projects to come to follow that. So we'll come back to this map now. These are the offshore wind projects under development. They're all listed here. And you can see, coming back now, the really, really big zones are here. And you may think, well, why don't you put them up here? Because the wind speeds are higher. But the sea is shallower here. So we have to think of the cost. Offshore wind is much more expensive than onshore wind, because construction costs are higher and you've got to get the electricity back by transmission subsea cables. But these are the really big areas. Dogger Bank. Look how big that area is. It's almost the size of South Wales. Look at that. Maybe 13 gigawatts from Dogger Bank alone. That's going to be very exciting. Right, let's talk about how it's going to fit into the electricity system. This is what we've got at the moment, okay? We've got 85 gigawatts of generation, because we need an overcapacity, because some power stations may be out for maintenance, so we can't just have 60 gigawatts. So all the advanced industrialized countries will always have a surplus, a plant surplus over and above maximum demand. And we've got a big spread now. We've got coal, we've still got coal, we've got some nuclear. We went big into gas because we've got the North Sea gas field, so We've been burning a lot of gas over the last 20 years in the UK. That's running out. Got some oil. Wind is coming in more significantly. We're also increasing our interconnections with mainland Europe. We've got a 2 gigawatt link to France. We've got a 1 gigawatt link that's just been commissioned very recently to Holland. There are other links planned to other countries. 2020, it's projected that wind is going to go up. Now, we don't really need 100 if it was conventional. Our demand in the UK, the economy is growing at sub 1%. You know, if the government would be pleased if the economy was growing at 1%. And even if it were to grow at 1 or 2%, with energy efficiency and savings, we are going to see a flat line of electricity demand in the foreseeable future. For the next 10 years at least, I would say. But we need more capacity because of the variability, which we talked about earlier. That wind is not always there. So we want to use the wind all the time whenever it's there, but we've got to make sure we've got backup when the wind is not there. The backup is seen in the form of conventional generation, not as storage. Storage is very expensive to build. The most effective methods of storage, and we have such schemes, we've got a 2 gigawatt pumped storage scheme. Now what that means, we've got 2 lakes very close to each other, and we've got a generating station which can pump water from the lower lake to the upper lake and store the potential energy in the upper lake and then release it. So it's a little bit like digging a hole in the ground and filling it back in again. It seems like a pointless exercise on one level, but on another level it makes incredible sense because you can store electricity when you have surplus and you can use it when you have deficit. And the efficiencies are around about 80%, 80-85%, so it makes sense. But how do we operate, and what are the impact of these wind farms on the transmission? What about operation? So here, I'm trying to tell a picture here to show what is variability. The red curves are showing the way that the electricity demand changes typically. You've got the daily variation, okay? You've got a weekly variation. These are the weekends. Yeah? And then superimposed beyond that, if we went into February, March, and so on, you'd see a seasonal variation. But it's very predictable, and mathematical models have been developed over many years which can predict electricity demand very accurately by studying social behavior and by knowing what happens when things happen. So big television events are a big problem for the electricity operators, but they know, so if there's a big football match or a baseball match, yeah, you know that demand will fall during the match because everyone's watching the telly and they're not doing anything else. And then the end of the match comes, everyone's going to do something like put the kettle on, and then you get this huge surge in demand. Now that's called TV pickup. But it's predictable. They know, 2 gigawatts pickup, yes, I'll get my pump storage plant to operate. No problem. It's all under control. But what about this? This is showing wind output from our current wind generators. So this is from a year or two ago. And you can see that the wind power, it's per unitized, okay? Up to 1 per unit here. Can go from virtually 0 up to 80% of its maximum. Now that's a big change. It is variable. It's not, some people talk about wind power as intermittent. Intermittent is the wrong word to use. Intermittent means sometimes it works, sometimes it doesn't. This is variable. This is variable power. And you can predict it. You can't predict it a long time in advance, but you can predict short term quite accurately with advanced weather forecasting models. And this is a really important thing for future operations, is that if you can improve the mathematical models of prediction, you can help to plan ahead, just like you can with a TV pickup. So it's not going to be a big surprise. So these people say, oh, what about when the wind is not blowing? Okay, we'll know. We will know when the wind is not blowing. So the electricity operators can manage the system. And they manage it, and this is how they're thinking now. This is projecting forward to saying when we're going to have 26 gigawatts of wind in 2020, they will have to adjust the output of conventional plant, and you can see it kind of follows more or less the daily patterns. But the wind variation is superimposed on that. And they will have to schedule power stations to come on and off more frequently. So flexible generation is important. But that's how it will be done, not by building another 10 or 20 gigawatts of storage. So the challenges of meeting high wind generation: sufficient thermal generation, in other words, conventional plant that you can control. You cannot control nuclear plant like this. We know that from examples in parts of the world where they tried it. They tried it in Chernobyl. They were exactly doing that. They were trying to do load-changing experiments in Chernobyl, and that's what happened. It went out of control. So nuclear plant is flatlining. You have to have enough generating stations that you can bring up and bring down in a good way. And CCGT, combined cycle gas turbine, is a good example. Fast response, flexible station. And we'll come back to that at the very end to see what we can do about that, because we do need flexible generation in the future. We need an increased transmission capacity. We've talked about Dogger Bank. How do you get 13 gigawatts of power from 200 miles off the coast? You can't use AC cables. You could possibly use DC cables, but DC capacity is not huge. Some research we're doing at Cardiff is into gas-insulated lines, big tubes filled with insulating gas. So these challenges are generating research projects at universities like this one, like Cardiff, like many of the top technical universities will be looking 10, 20 years ahead at trying to think about new engineering solutions for future energy challenges. Demand-side control measures. What does that mean? This is a phrase that's used a lot. Demand-side. It means the consumer. You know those load curves we just looked at? Most of that, or rather, most of that is because of our habits. We use electricity unconstrained. Nobody tells me I cannot turn my computer on or off, or my kettle. We use it as we like. It's there. We take as much as we need, and that's it. And we don't waste it because it costs money, but we use it freely. What about if we control the usage? Now that usually horrifies people. They think, oh, the big brother is telling me that I cannot control I demand the right to use my electricity whenever I want to response. But we don't really mean that. We mean, can we control it in an intelligent way? Maybe we can incentivize people to put their washing machines on at night time. Electricity we could make cheaper in the night. So suddenly people say, I don't mind doing that because I'm not paying so much. Or big industry, and this already happens, big industry have industrial processes with large thermal time constants. Very often they can say, well, yes, if you give me £500,000 back in my electricity bill, I will, at short notice, I can reduce my demand. So demand-side control measures will be important, and when the system becomes smarter, because with modern communications now and computational speed that's available and modern control systems, we can get sophisticated, smart grid operation. You may have heard of this term, smart grid. It means lots of things to different people, many things to many different people, but ultimately it means about having greater control and flexibility over the power system, including controlling demand. Now, coming to the end, Professor. I hope I've kept within time. You've seen what we have in the UK. You've seen what the plans are maybe 5 to 10 years down the line, or at least 2020 we talked about. Now what happens beyond that is much more uncertain. But let's take a little look at what is a possible scenario looking forward to 2050. Now obviously the government, Department of Energy and Climate Change, the large electricity bodies, National Grid, who look after the UK electricity system, they're looking ahead. They have long-term planners, strategic long-term planning. Occurs at government level, occurs at industry level. And they've looked at scenarios. Now this scenario, which has been developed by National Grid, based on a government idea of what they call a strategy of gone green. They call it the gone green strategy. What does that mean? It means that we've really gone in a big way to meet all the emissions targets, and we will virtually be operating in a green economy. That means it will be totally different to the way that we're experiencing life now. Just like I told you about my parents, when they grew up, they had no electricity, no running water in the house, and then they grew up into the society that we see now. Our children, and their children's children, will see by 2050 something completely different to what we're experiencing now. That will be the degree of change that we're looking at. And it's worth spending 1 or 2 minutes with this graph, because I think it's a phenomenal graph to encapsulate what we hope to move to. Here we are now. On the left-hand side, we've got energy consumption here. Okay, so we've talked a lot about power capacity, and we've also talked about energy. So this is really how much energy we are consuming in terms of electricity. Okay, it's not the wider economy of heat and transport, it's just electricity. The orange here, and we're around about 380 terawatt hours a year in the UK, okay, from the electricity, 380 terawatt hours. Unabated thermal generation, what does that mean? It means coal-fired power stations, gas-fired power stations, oil-fired power stations, biomass-fired power stations. It means when we're burning carbon, and up the chimney is going carbon dioxide. That's what we mean by unabated thermal generation. And you can see that even though we talk a lot about renewables, we talk a hell of a lot about renewables, where is renewables here? It's tiny, isn't it? It's still tiny. This is the green, okay? Non-thermal renewable generation is the green. Okay, we've got a little bit better now. We can see the step change here. We really are starting to pay a little more than lip service to renewables. We've got nuclear, yeah. Nothing big changing there. But now, to 2020, what we've seen, we need to reduce conventional generation. How do we do that initially? We increase the renewables, and wind is going to be so big in this. So our little triangle growing there, our wedge through to 2025 is green. So we've still got unabated generation, a lot of wind, and we're still keeping nuclear an element of nuclear. We can't go fully nuclear, because if we want wind, we can't have just wind and nuclear, because we can't change the nuclear output. So we need the orange stuff for the controllability, the variability, the operational reserve. Now, beyond 2025 is the really interesting thing. Remember I said about the flatlining energy use from electricity? Our demand is not going up. Okay? The economy is growing very slowly. Efficiencies are increasing. So really, we're not going to be seeing major increases. We're going to be flatlining in demand. But then we see something interesting happen. We have a fundamental change in society here, 2025 through to 2050. What's happened there? It's when transport is going electric. Electric vehicles. We are probably going to see our cities full of electric vehicles. We are going to see virtually heating from gas. I mean, if you go to the UK, most of the houses are heated from gas boilers. With central heating from burning gas. That's going to go. We're not going to have it. We're going to have electric heating. We may have heat pumps. We may be sophisticated, have underground heat pumps. But we're going to go electric. So this increase in electricity usage is not the economy growing. It's a shift in social pattern in terms of what we are using for heat and transport. And this is the really interesting thing, combined with one other very important aspect which is projected, which is carbon capture. You can see now the grey wedges, carbon capture and storage. That's when we're talking about burning carbon-based fuels, but we will capture and store the CO2. And it's projected that by 2040, unabated thermal generation will not be present. And finally, at 2050, we have got a very different picture from what we're looking at previously. Renewables, of which wind will be such a big part in the UK. Nuclear will have grown, but we still have a very important element, and maybe it will be biomass in the main. But that would be a carbon capture storage system. 2050, a long time ahead, but a complete revolution in terms of from where we're starting now today. So you can read the summary yourself. And that's my view. I've done a lot of reading over the last couple of weeks in preparation for this, but I try to get the latest figures.
Yeah, thank you.
To give you a picture. Okay, it's similar in many other European countries, yeah, and outside Europe as well, and the US I think is catching up on this as well. But I've tried to give you a real flavour from what is happening in the UK. Thank you for your time.
Yeah, thank you very much. We have any questions to Sarita? No. Any questions?
Well, I have one basic question actually. Thanks for the presentation first of all. And there is no doubt that the policy direction is really important, which was showed on the last slide. But I was wondering, regarding these very big, large-scale projects on construction of offshore wind farms, what is the source? I mean, what is the estimated cost of such projects, and what are the sources of this? If it's, I mean, very big project, obviously it will require not only support from the government, but deep involvement of the private sector. And what are the conditions for that?
Yeah, I had a slide on the costs, and I don't know where it's gone. Yeah, can I borrow this for a second? In the paper, you see that costs. economic considerations. Yeah, I had a slide which was, I don't know what's happened to it, but it's showing the costs of on and offshore wind in comparison with other emerging technologies. So photovoltaic, there's a big project just near Cardiff, the barrage. You see, in the UK we've got a very large tidal range. It's the second highest in the world in Cardiff, where I come from. So the sea comes in and goes out many metres. So there's an idea to build a 10 gigawatt barrage to generate electricity. And that has to be compared with wind, you know. Then there's the photovoltaics. Then you have tidal stream generation. You have supercritical coal generators that are being developed. So there's a lot of alternative, futuristic generation which has to be compared economically. So the costs, I mean, the costs are normally specified in terms of either pence or cents per kilowatt hour, okay, or dollars per megawatt hour. Okay, that's the way in which these costs are normally stated. If you're talking to consumers, domestic consumers, you say cents per kilowatt hour. If you're talking, you know, in terms of the governments, they often talk in terms of dollars per megawatt hour. So it's a cost of 1 unit of energy from each source. Now, these economic calculations, how do they do them? They're quite simple, really. Are economists here, people who've done? Yeah. Well, they use a technique, a simple technique, usually, because you can't be too accurate thinking of the future, because the uncertainty in the quantities is so great. You don't need highly precise calculations. So they use net present value technique. Have anyone heard of that? Sometimes it's called discounted cash flow technique, NPV or DCF technique. So what they do, they will take the capital cost and then they will annuitize the energy cost effectively over a period of the lifetime of the project. So that could be 40 years, it could be 60 years, it could be more. And then, based on the fact that £1 now, $1 now, €1 is not going to be the same as €1 in the future. Yeah? It's better to have the £1 now than the promise of €1 in the future. So money now is worth more. Money now is worth more because you can invest it and make more, or you can put it in a bank. Okay, interest rates are historically low at the moment, but so you have to do a calculation which takes into account the value of money over time, and with wind and other renewables, what you have is a very, very high initial capital cost. But obviously the running costs are lower, primarily because the energy cost. The fuel cost is zero, and all you have to work in is maintenance costs, which could be high. And on the basis of that, I mean, my experience, because before I was an academic, I used to be an engineer, okay, so this is how I used to do these calculations for engineering projects when I worked for the National Grid Company. And my experience in such calculations is that you can almost get any answer you want.
That's the problem, yes, I know.
You know? This is the truth, because if you assume, who can say what the interest rate will be in 10 years? Or what will the inflation rate be in 5 years? You really don't know. So you have to treat these figures with a pinch of salt. Okay? This is the truth. This is my opinion about this. But for now, we've got, bearing in mind what I've just said, these figures came from a large engineering design company, Mott MacDonald, and they say that £83 per megawatt hour for onshore and double for offshore.
And how about they say other existing one?
Interestingly, the same report, they say that, this is from memory now, that the barrage, I think they said was 700.
My God.
Now, I disagree with that.
Sure, me too.
Because I think the barrage is more or less the same as wind.
I believe so, yeah.
So this is, to answer your question.
Yeah, but already
I haven't answered the question, but I have an